Then we can have a look at the Spark data structure.
In this part, we will learn the core concept of Spark, which is RDD. RDD is short for Resilient Distributed Datasets. RDD is abstraction of the basic data by Spark. We have learned HDFS. HDFS stored data by block. And similarly, RDD also can be seen as the collection of data. So how does RDD generate? RDD can be created from a Hadoop file system or a storage system that Hadoop is compatible with, such as HDFS. Alternatively, an RDD can be converted from a parent RDD, which is the last RDD of it. For example, there are two RDD, RDD1 and RDD2. If the RDD2 losses, we can find the RDD1, which is the parent RDD of RDD2, and reoperate the method to generate the RDD2. Does that make sense? We call it the lineage of RDD. And this feature also makes sure the high stability of Spark. Besides, user can choose different storage levels. 11 levels available to store RDDs for reuse. RDDs are stored in memory by default and overflow to disks in case of insufficient memory. RDD partition. RDD partition is required to reduce network transmission costs and implement distributed computing. RDDs are partitioned according to each record key when efficiently joined in two datasets. It's worth mentioning that RDDs are read-only and static. Therefore, Spark can provide a higher fault tolerance capability and implement speculative execution. The speculative execution can make a plan of computing in advance and complete the parallel calculation in a specific time period. It's pretty abstract. Let me give an example. We all have taken an airplane. So before the aircraft takes off, has there already been a flying plan or schedule? Of course, yes. Before the plane takes off, the estimated departure time and arrival time have been determined. Even each point of the route are certain. Before the departure time, we have already known when to take off and how to fly. That is the speculative execution. There are a series of dependencies between RDDs, which are divided into narrow dependencies and wide dependencies. The left side of graph represents the narrow dependency, while the right side represents the wide dependency. Narrow dependencies represent that each partition of the parent RDD is used at most by one partition of the child RDD, 1-to-1 or many-to-1. By contrast, for wide dependencies, each partition of the parent may be used by multiple child RDD partitions, which is the basis of stage division. So it's 1-to-many. So the narrow dependencies can be seen as a single child family, and the wide dependency can be seen as a many children family. It's easy to memorize. The dependency can also be indicated by the lineage, which is an RDD remembers how it's involved from another RDD using a lineage. Wide and narrow dependencies are also different in fault tolerance. Obviously, for the narrow dependency, if one child RDD is lost, only the parent RDD partition corresponding to the child RDD partition needs to be recalculated. In contrast, since the child RDD partition in one wide dependency may use multiple parent RDD partitions, which means when one child RDD lost, there will be more parent RDD partitions need to be recalculated. In extreme cases, all parent RDD partitions need to be recalculated. The figure also illustrates it. Obviously, it's wide dependency. If the B1 partition is lost, A1, A2, and A3 needs to be recalculated. But actually, some data should not be included because part of A1, A2, and A3 may be used by another child RDD, B2. That is the difference between two dependencies we have mentioned. Besides, for a wide dependency, the partition of the same parent RDD will be involved in the calculation for different child RDDs, which means that it needs to be transferred to different child RDD partitions. This may involve data transformation between multiple nodes. In contrast, the partition of each parent RDD on which narrow dependency exists is transferred to only one child RDD partition. Generally, the conversion can be completed on one node. Actually, the stage division of RDD also bases on different dependency. It's very difficult to divide stages in a submitted job due to complex RDD dependencies. Spark Scheduler reversely traverses the whole dependency chain from the end of the directed acyclic graph DAG. When shuffle dependency, also called a wide dependency, is encountered, the dependency chain will be broken. When a narrow dependency is encountered, the RDD partition will be added to the current stage. The number of tasks in a stage is determined by the number of RDD partitions at the stage end. RDD conversion is a partition-based cross-grain computing, and the result of a stage execution is the RDD of these partitions. Then we will introduce the operation types in Spark, mainly two steps: transformation operators and action operators. Do you remember the operators of MapReduce? Actually, there are only two operators in MapReduce: map and reduce. By contrast, there are plenty of operators in RDD, which can be divided into two types: transformation operators and action operators. The transformation are invoked to generate a new RDD from one or more existing RDDs. So the transformation operators are lazy in nature. They will be executed only when some actions performed. The typical transformation operators are map, fatMap, filter, and reduce by key. By contrast, a job will be immediately started when action operators are invoked. Well, you can regard the action operator as the director of a field, and the transformation operators are like the script of the field. The script shows the plot of the movie and how actors perform. Only when director says action, actors can start their performance. All the transformations adopt the lazy strategy. The computation won't be triggered if you submit a transformation functions only. Instead, the computation will be triggered only when you submit the action function. This table shows some common action operators. In this part, we have learned some important roles in Spark like RDD and the different dependencies. Next, we will learn the different formats of data in Spark.